Now that we have some bits and pieces of how we work with symmetric orthonormal matrices, we're ready to go to the next step of image compression, which involves something known as the singular value decomposition. Now, we've already encountered one decomposition before, when notably we dealt with the diagonalization theorem, which applies only to square A matrices. By square, we mean n by n. And in our case, we could decompose A into this product of x times d times the inverse of x, this product of three matrices, where D is the diagonal matrix with eigenvalues along the diagonals, and X is the matrix of corresponding eigenvectors in the same order as the eigenvalues in their respective matrices. Now, this works great when our matrices are square. But what if our matrices are not square, such as a matrix representing an image? Well, for this, we have another type of decomposition, which is very similar in structure. It's called the singular value decomposition. And this theorem states that any non-zero real m by n matrix, okay, now real is primarily what we've been dealing with. There are matrices called complex matrices, but for now we're assuming that all of our components are real, which makes sense. Now we assume that this has rank bigger than 0, meaning that the matrix contains at least one column that is not entirely full of zeros. If it is, then this theorem is going to fail. So rank means the number of linearly independent columns. So it has at least one non-zero column. So as long as it has a 1 in there somewhere, then we could consider that matrix to have rank r greater than 0. If it consists of entirely 0 vectors, then the 0 vector is a set containing the 0 vector is never linearly independent. And moreover, if you have all columns of zeros, then you don't have a basis. You can't span any space whatsoever. So this decomposition says that A can be split up into a product of, again, 3 matrices, but the 3 matrices are going to be a little bit different than they were when we had a square matrix. A can be decomposed into the product of a matrix called U, a matrix called sigma. This is sigma. It's not representing summation in this case, as you might be used to. It's just the name of the matrix. And then this V matrix, it will be the transpose of this V matrix. Let's take a look at some dimensions here. So U is going to be an M by M matrix. It's going to be a square matrix with orthonormal columns. Okay, that's going to be key here. They need to be orthonormal columns. Sigma is a diagonal matrix that contains along its diagonals these sigma values, which we'll come back to, and that's going to be an M by N matrix. And V transpose is an n by n matrix such that V has orthonormal columns. So lots of orthonormal in here. So to construct these dimensions, U, we're saying, is going to be an m by m matrix with orthonormal columns. So we'll just go ahead and call these vectors in here U1, U2, and depending on how many columns, how big M is, this will contain M of these columns. And each of these vectors is going to be M by 1. This will be an M by 1, M by 1, M by 1, because it has to have M rows, and then it will have M of those column vectors, so this will be an M by M matrix. Now, sigma is going to be a diagonal matrix, meaning that it's going to contain these values called sigmas along the diagonals, and it's going to contain n of them. And it's going to contain zeros everywhere else. So it'll be 0, 0, 0. There's going to be zeros all the way everywhere except along that diagonal. So we see that that's what we mean by a diagonal matrix. It's only going to have non-zero values along the diagonal. That's going to be an M by N matrix. It's going to have M rows and N columns. And then V transpose, V is going to be an N by N matrix. Therefore, V transpose is going to be an N by N matrix. And that's going to have N columns, V1. This will be the transpose, the transpose of V. So V, we could write as having the columns V1 through Vn. And when you transpose that, the columns will become rows. Therefore, this first row will be V1 transpose, and all the way down to Vn transpose. And that will be an N by N matrix. So let's check the dimensions. We said that A was M by N. What we get here is the first product is an M by M times an M by N. So that's going to produce an M by N matrix. And next, that's going to multiply this N by N matrix. Inner dimensions match. So the product, the final product will still be an M by N matrix. So at least we know the dimensions work out. Let's think about how we're going to form these things. Now, we're not going to provide a lot of justification here. We're just going to state the procedure, and then in a future video, we will actually look at why this works out. So this factorization is called the singular value decomposition. Again, has a similar structure to the diagonalization that we've uncovered before. So how do we construct these matrices? Well, the first thing to note is that U and V are not going to be unique, meaning there's more ways than one to find them. But our process allows for more algorithmic or orthonormalization, which allows a computer to do it in the same way each time. So we're going to just state this stuff as facts. So let's start off with a matrix that's not square. This is a 2 by 3 matrix that we have here. And also I want to point out that since these are numerical values, we can think about these as being colors. So if I represent that 2 by 3 matrix as a 2 by 3 grid of pixels, we'll say the value of 2 kind of is this yellowish orange, a little bit of an orange pixel. Zeros mean that those are pure white. The 4s mean we kind of get a little bit more of an orange, and 2, we can see that those 2 pixels are the same. So let's pretend that this is an image for now. And the first thing that we're going to do in order to execute this is to find the eigenvalues and eigenvectors of A transpose A. We're going to call them lambda i's and vi's, where I goes from 1 to n. The strange step here is that we're finding eigenvalues and eigenvectors of a different matrix than the A matrix that we're interested in. But the decomposition will apply to A as well, as we'll soon see. So step 1, A transpose A. There's the transpose of A times the A matrix. We end up with a square matrix. And notice that this is first of all, a 3 by 3 symmetric matrix. We see that it's symmetric. Every column is the same as its respective row. Second column is the same as the second row. Third column is the same as the third row. So there's our symmetric theorem at play. Next, what we're going to do is we are going to find the eigenvalues and eigenvectors of this matrix. Using technology, we would find that sigma 1, sigma 2, and sigma 3, or lambda 1, lambda 2, lambda 3 are 28, 12, and 0. And then I get some eigenvectors. And what I'm going to do is I'm going to normalize them, because they are going to constitute our U matrix. So in our U matrix, we stated that it is going to have orthonormal columns, and same thing with V transpose. I think I said that these are going to go into U. They're actually going to go into V. All right, so that once we have that step, the next thing is to form sigma. Now, how is the sigma matrix going to be formed? Well, it's going to be formed by taking the square roots of the eigenvalues. So basically the sigmas are just the square roots of our eigenvalues. You might have heard me say sigma by accident up here when I was referring to lambda because they're closely related. So the sigma matrix, recall, is going to be an m by n matrix. A is 2 by 3. That's our m and our n. So this is also going to be a 2 by 3 matrix. The sigma matrix is the same size as A. Now, I have 3 eigenvalues, but I only have 2 rows. So here's an interesting thing. Sigma i's are often referred to as the singular values. If we run out of eigenvalues to get the full dimension of the matrix, pad the remaining diagonals with zeros. Omit 0 eigenvalues. So this takes care of our case where we have more eigenvalues than we do rows, and therefore we can't put the square root of 0 down here because that would give us a third row, but it's only going to be a 2-row matrix. So along the diagonals, we're going to put the square root of 28, the square root of 12, and since we've run out of rows, we're going to omit that third eigenvalue. Now the interesting part is that if you might say, well, what if this is not 0? The good news is that if we run out of space, then that's going to imply that the remaining eigenvalues are 0. And zeros really don't impact multiplication. All right, there's our sigma matrix. If we ended up here with fewer eigenvalues, like if we had only had 1 eigenvalue, say 28, then along the remaining diagonals, we would just place or pad with zeros. Next thing we're going to do is we're going to form the V matrix, and we're going to organize the normalized eigenvectors of A transpose A in the correct order. So that was, we computed our eigenvectors, we normalized them. Normalization, remember, that just means that we're going to take V1 and divide it by its magnitude. In this case, the magnitude of V1 would be the square root of the sum of the components squared, which is V1 over, that's going to be 1 plus 4 plus 9 is 14. And we'll do the same, already did the same thing here for V2 and V3 to save some of that work. And next thing we're going to do is we're just going to take this first column here and place it as our first row in the V transpose matrix, right? Because V is going to contain the columns, the eigenvectors as columns, but V transpose will contain the eigenvectors transposed as its rows. And so here is V3 transposed. Okay, so really weird stuff, but we're going to go with it. This is a procedure that we're setting up here. And the last thing we have to do is we have to form U, where U equals a set of columns. And in this case, I'm referring to them as P1 through PM, these column vectors, where the ith column is found by taking the A matrix, multiplying it by the corresponding eigenvector of A transpose A, and then divided by sigma I. So here's our A matrix. This right here is going to be V1. That's our, you can see here, first row of V transpose. I multiply those together, and then I divide by the corresponding sigma I, the square root of the eigenvalue corresponding to, this is the square root of lambda 1, square root of 28. And I end up with this matrix here, this vector here. That's going to be my P1 vector in that matrix. I'm going to repeat the same thing because I have a second non-zero eigenvalue. Now, also point out here, we only take the m vectors that have non-zero singular values. So recall that lambda 3 is equal to 0, and so that is not going to constitute a column in the U matrix. So again, here is A. This is V2. And down here, I have the square root of lambda 2, which is what we refer to as sigma 2. And I get this column here. And that's basically what our second column will be in that matrix. So here we see we just put those together to form the U matrix. There is the first one. And here is the second one. So I'm done now. I have formed the three matrices that were required. So now what? Well, let's check our work. Let's make sure that if I take the U matrix, which is this one here, times the sigma matrix, times the transpose of the V matrix, again, these rows are just three eigenvectors of A transpose A. Then I multiply these three together, and what should I get? Well, I should get my original matrix back. So it worked. At least it worked for this case, and the good news is that this theorem holds for any non-square matrix. So next we might wonder, how is this in any way going to help us compress images? And that's what we'll do in the next video.